Hi, this is my video number 20. In this video, I'll talk on convergence of series. Convergence of series. So what we're going to do here is that I'm going to state some of the properties of the convergence series, and we will discuss about that. Okay, so look at the first theorem. So if the series converge, if the series that un converge, then we have limit of un is equal to 0 where n goes to infinity. If the series converge, then limit is 0, or in short I can write this as if the series converge, un converge to, let's say, some numbers u, then limit n infinity un is 0. Okay, but the other way around is not working. Okay, means that if the limit 0, that it's not necessary that our sequence converge. But if you converge, then definitely the limit goes to 0. But if the limit 0, not necessarily series converge. And if the limit un different than 0, then our series definitely diverge. Okay, so let us prove this. Okay, we prove this. It's not difficult to prove. So let's consider the partial sum of that Sn. So un equal to u2 equal to un plus u2 plus up to un. Okay, and Sn minus 1, this is u1 plus u2 plus u3 plus up to un minus 1. So if you take the difference between those two sum, so we have Sn minus 1, so therefore we have those n, this equal to, so you can see u1 is 0, that one is 0, un minus 1 is 0, what left is un, so we have this is equal to un. Okay, since our series converge, since series converge, which means the limit of the partial sum exists. So which means I can write the limit of the partial sum exists. So let's say this is equal to n. So l equal to some number l. No, I put it here u. So I put it here u. Okay. So this is also with n plus 1. There's no difference because the series converge. Okay. So therefore, if I take limit both sides of this, so we take a limit of Sn minus 1. Okay, this is the limit of un. Here we can write limit Sn minus limit Sn minus 1. Okay, which is limit Sn is, we show that equal to u, so we have u minus u, that gives you 0. So therefore limit of un n infinity that equal to 0. So with that we have proved that the convergence series, so the limit is 0. Now, but the other way around is not true. So if the limit, but I would say if the limit un equal to 0, n to infinity, that not necessarily the series converge to u. This is not always happen. not always happen. So let's see some contradicting example. Look at this example. You consider that series. Okay, definitely if you take a limit of 1 over n, alright, it's equals to 0. Yeah, this is the limit un. I put this way, limit un. This is limit 1 over n, then limit 1 over n, that equal to 0. But this series diverge, but 1 over n diverge. So let's show that this series diverge. Okay, so if you consider the partial sum up to 2n, so that will give us 1 plus 1 over 2, 1 plus 1 over 3, 1 plus 1 over 4, and so on, up to 1 over n plus 1, 1 over n plus 1 over n plus 1, and so on, up to 1 over 2n. Okay, and if you take a partial sum of up to n terms, so this is 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 up to 1 over n. Okay, take the difference between those two, so therefore 2n minus Sn, that give you can see if you take the difference, that one is cancel out, that cancel out everything, so that cancel out, what left is 1 over n plus 1, 1 over n plus 2, and up to 1 over 2n. Okay, and we know that for n plus 1, this is less than 2n. We know this. Alright, but if I inverse this, 1 over n plus 1, that becomes greater than 1 over 2n. So we use this fact to here. So what we have, that is greater than, for that it should be greater than 1 over 2n, that should be greater than 1 over 2n, and so on, up to 1 over 2n. That give us, put it here, n over 2n, that give us half. So what does it mean? So it means that the sequence of the partial sum, does not satisfy the Cauchy condition. You know what Cauchy condition is? I have defined this thing. So therefore, Sn does not converge. Okay, what is Cauchy condition? Given any epsilon for the convergence, because Cauchy sequence is always converge. So given any epsilon positive, given any epsilon positive, you can find n positive such that the difference between Sn minus Sm less than epsilon for all n m greater than some number n. We can also, so this is the Cauchy condition. So here, look at this. So in our case here, our n is 2n, our m is n. So it should be less than epsilon, but in our case, we show that it's greater than half. It's quite a big number and bigger as well. So therefore, this is the sequence of the partial sum does not satisfy the Cauchy condition. So therefore, this Sn does not converge. There is an alternative proof for this, but I don't want to stress on that. So let's see some of the a contra example, which means if the limit is different than 0, then the series diverges. Yeah? So let's see those things. We say contra example, contra positive. Example. So if contra positive example means it means that if the limit of un different than 0, then that series diverge. Okay, remember that in the theorem we have, if the series converge, the limit is equal to 0. But if the limit equal to 0, doesn't mean the series converge. But for the case of the limit is different than 0, then definitely our series diverge. Okay, look at example. Consider this example, 1 over n plus 1. Okay, if you take the limit of this, take a limit of n over n plus 1, yeah, n goes to infinity, this is equal to 1. Yeah, you divide by the highest power of that, then you got 1. So which is different than 0. So therefore, that series n over n plus 1 diverge. Okay. Look at the second example. If you have, let's say that series 2n over 2n minus 5, this is also diverge. Why? Because if you take the limit of 2 to the n over 2n minus 5, this is n goes to infinity, limit everything. Okay, this equal to 1, which is different than 0. So therefore, those series 2n over 2n minus 5, this is diverge. Alright, and we have some example. If you can find in many books that we have this kind of example, many example you can find in the book. 3n minus 1, this is another example. 4n minus 5, this series also diverge if you take a limit 3n minus 1, 4n minus 5, n goes to infinity, that will give us 3 over 4, which is different than 0. Okay, so therefore our series 3n minus 1 over 4n minus 5 diverge. Okay, now again I have mentioned earlier that we have this theorem. Remember that we have this theorem. The theorem says that if the series converge to some number u converge, then the limit of un is equal to 0. Okay, but if the limit un is equal to 0, doesn't mean that un converge. It could converge, but it could not converge. So we cannot make any decision or conclusion. Yeah, cannot make any conclusion. Just based on the limit of element un. But in another case is that if the limit of un different than 0, then in this case un diverge. So we have a couple of cases there, and just based on this first theorem here, so we have a couple of other cases. Now look at the example for that. For this case, we have seen that example. Now look at those examples. So let's see example number 1. 1 over n. This series diverge. Okay, I think we have shown this series diverge. Okay, but if you take a limit of this 1 over n, that goes to 0. Okay, so you can see from here, if you take the limit equal to 0, but the series converge, so it seems that this theorem is not true. Not that the theorem is not true, but the inverse is not true. Okay, the inverse is not true. If the limit equals to 0, it's not necessarily our series converge. Okay, other example we can look at. Let's say this log n, this also diverge, but the limit of 1 over n log n dash equal to 0. Okay, and then what about this series? 1 over n squared. Okay, this series converge. This is converge. But if you take a limit of 1 over n squared, this also gives you 0. Okay, so you can see here, if the series converge, definitely the limit goes to 0. But if the limit goes to 0, not necessarily it's converge. Okay, some of this proof of the convergence we will give later. Now look at the couple of simple properties. We have a theorem. So let un converge, vn converge. Okay, we have two convergence series. Then first un plus vn, this is equal to un plus vn. How to read this? The summation of two series is equal to this summation of the summation of two series is equal to the summation of each series of the summation of the series. Series of the summation of the element of that series. Okay, that's the first one. The second one, we have C for any constant C, un, this is equal to C un, and we have number 3, A un plus B vn, this is equal to summation of A un plus B vn. All right, if you observe this, basically the properties number 3 here is the combination of property number 1 and number 2. If you can prove that one, we can prove that one, then this one will follow automatically. So let me prove the case number 1. I'll leave it the rest to you. Proof for number 1. So we let our series un converge to u and vn converge to v, and we let the partial sum of series, the first series u as Sn, so we have u1, u2 and so on up to un. We take the second series, the partial sum we denote as Tn, so let's say this is v1, v2 up to vn. Okay, then if we add up these two series, that we have this, Okay, we add up these two series. So add up the first the partial sum of that. So then we add up those things, Sn plus Tn, that will give us U1 plus U2 plus Un plus V1 plus V2 plus Vn. Okay, this is equal to U1 plus V1 plus U2 plus V2 and so on plus Un plus Vn. Okay, now if we take a limit, what will happen if we take the limit of Sn plus Tn? Okay, from the properties of limit, we can write this as a limit of Sn plus limit of Tn. Okay, we know that this series converge, so it means its partial sum also converge. So the limit converge. So we have this. The limit of the partial sum is equal to U. The limit of partial sum for the second series is equal to V. So which means the summation of the first sum is equal to U, because it's converged to U. This is Un, and that is Vn. Okay. And if you look at here, so what do we have here? This is actually summation of Un plus Vn, isn't it? So if we take the limit of those, limit Sn plus Tn, this is equal to, take a limit of those. Alright, this is summation of Un plus Vn. Okay, so limit of this equal to that, and we also have shown that the limit of this equal to that, which is that. So therefore Un plus Vn, this equal to summation of Un plus Vn. So that's the proof, end of the proof. Okay, now let me give an example. Show that 1 plus 1 over 3 plus 1 over 6 plus 1 over 10 plus 1 over 15 and so on, plus 1 over n plus 1 over 2 and so on, this is equal to 2. How can I prove this? This is quite interesting series, right? So that equal to 2. Alright, so as a solution, so consider the partial sum of that, Sn, up to n terms. So we have 1 plus 1 over 3 plus 1 over 6 plus 1 over 10 plus 1 over 15, okay, and so on. This is up to n plus 1 over 2. Okay, if you bring this to the other side, Sn, so what we have, this is half of Sn. So we have 1 over 2 plus 1 over 6 plus 1 over 12 plus 1 over 20 plus 1 over 30 plus so on up to 1 over n plus 1. And basically we have shown that each n plus 1 can be written as what? N 1 over n plus 1. I think we have shown this. This is equal to 1 over n minus 1 over n plus 1. we have shown this. So which means each of these terms can be written as 1 minus half plus 1 over 2 minus 1 over 3 and so on up to 1 over n minus 1 over n plus 1. So we look at that. If you observe this, if you have minus half plus half, those cancel out with that, this cancel out with the term before that. So what left is 1 minus 1 over n plus 1. So therefore our Sn is equal to 2 minus 2 over n plus 1. Now if you take a limit of this Sn, that will give you, we take a limit of right hand side 2 over 2n plus 1. Alright, limit of this 0, limit of 2 is equal to, so this is equal to 2. So we verify that the series of this is equal to 2. So in this video, I've shown you, or I've give you the some of the properties of the series, convergence of the series, how to test for the convergence, at least for the moment, right? We have, after this, we have a convergence test to determine whether the series converge or diverge. All right. For this case, you need to remember 3 things. The main theorem that I have given today is that limit if the series converge, if the series converge, then the limit of un is equal to 0. But the other way around, we cannot make any decision, which means if the limit is 0, it's not necessarily the sequence converge. But if the limit different than 0, then definitely the series diverge. So we have 3, from the one theorem we have two other, the consecutive over there. So we have 2 other result that you need to remember. So with that, thank you.